Hello. In this video, we'll be taking a look at the first published research by Maxwell Plus. This work was presented at the Women in Machine Learning Conference at NeurIPS in 2017. The primary author on this paper was Rebecca Simpson, who was leading our ML research at the time. This work looked at problems in transfer learning and potential ways to avoid the phenomenon known as catastrophic forgetting. To understand what that means, we can think of how humans learn. Many of the things we do are some combination of skills we've learned in the past. Once we learn, for example, to differentiate between a truck and a car, we can apply similar skills to learn the difference between an SUV and a sports car. On the other hand, many AI models, especially at the time of this publication, couldn't transfer these skills effectively. A model could be trained on vast amounts of data and then be fine-tuned on a new problem. This allowed the model to perform well in situations where there was limited labeled data. Medical data, in general, is one area where this is very common. Unfortunately, however, when transfer learning onto a new dataset, AI models would often forget what they had learned about the original data and perform poorly on that original task. It would be as if we suddenly forgot how to spot a truck. For this project, we designed and extended a version of traditional transfer learning, which allowed the model to retain its original weights and learn a sparse collection of weight changes to enable performance on this new task. To test this new method, we designed two experiments. The first of these experiments was to train the model on data from CIFAR-10, a large, publicly available, simple dataset, in two phases. Each phase contained a different subset of the CIFAR classes, and by adjusting the ratio of classes in each stage, we could simulate various transfer learning scenarios. These spanned from having 90% of the data in stage 1 and transferring onto a small new problem, to having only 10% of the data in stage 1 and transferring onto a much bigger, more complex problem in stage 2. To assess this, we trained 3 models. One with all of the data from CIFAR-10 to use as a benchmark. One using traditional transfer learning, which adjusted only the final dense layer, but froze the other weights, and using our method as the third model. What we found is that our method showed equal or better accuracy than traditional transfer learning. And this was especially prominent when the first training stage contained only a minority, 10% of the classes. From this, we can see that traditional transfer learning on too small an initial dataset can limit the further potential of the model and its ability to effectively transfer learn. In the second experiment, we looked at augmenting the transfer learning data with a small subset of examples from the original data. In this case, it was a combination of data from the MNIST dataset and the CIFAR-10 dataset to give two quite different datasets. The hypothesis here was that reminding the model of its original task may help constrain the weight changes that happen during transfer learning and help it retain some of that previous knowledge. We tested everything from a single to 1,000 examples from the original training set and found that both traditional transfer learning and our new method benefited from these reminders. Our method, however, was able to use these reminders much more effectively. It showed increased performance with only a single example from the original dataset, allowing us to maintain high performance in both the original and the second task that model had been trained for. Overall, this work set the foundation for much of the work that has happened since 2017 at Maxwell Plus. As the medical field is rich with raw data, but scarce in labels, companies like Maxwell Plus need to adapt the way we train AI to make use of the data that we have to achieve the performance necessary to provide real clinical outcomes.